Hello, Soul. Hello, colleagues and friends. My name is Hans-Georg. I'm in Heidelberg, in Germany. I was a member and also chairman of the ICRU. My co-author is Thomas Otto from CERN. He's a current member of the ICRU. I've been invited by the Congress to give a presentation on this topic, and I would like to thank the organizers for having me invited. The topic is the ICRU Report 95, or in more general terms, new definitions of the operational quantities for the assessment of effective dose. I will not talk about operational quantities for other quantities, particularly not for those dealing with tissue effects. My presentation is divided in three parts. I will talk about the present situation with operational quantities with regard to effective dose. I will then introduce and shortly the new definitions and some of the details of them. And finally, we'll discuss potential consequences for radiation protection dosimetry using this new quantity. The effective dose is, like everybody knows, the central dosimetric quantity in radiation protection. It has been introduced by the ICRP in 1977 in ICRP 26. In the same report, the three principles of justification, limitation, and optimization were introduced, and particularly the last two, limitation and optimization, need, of course, a quantitative tool to be implemented in practice. The new quantity effective dose, in fact it was called at that time effective dose equivalent, had very interesting features and was very welcome. Is applicable for both external and internal exposure. It can be applied to any type of radiation, and it is a quantity for the whole body and therefore very suitable for both the optimization and the limitation. I assume that everybody knows the definition of effective dose. Nevertheless, I would like to point to some special aspects of it. The absorbed dose in the definition is the average dose, the mean dose of organs and tissues, which are specified by ICRP. These absorbed doses for organs are weighted by radiation weighting factors, and this weighting of the absorbed dose results in a quantity which is called equivalent dose. Then the weighted average of equivalent dose, the tissue weighted average of the equivalent dose, is then the effective dose. Here in this scheme is an attempt made to explain how that is calculated or how it's evaluated. Starting off with the exposure situation for external and but also for internal radiation. One has two types of reference phantoms, a male and a female. They have been established by ICRP and ICRU and published in ICRP report 110, and with the help of the radiation transport calculations, first of all, the mean absorbed doses in each of the organs and tissues is calculated. Then the radiation weighting factors are applied to result in the equivalent doses for both sexes. These equivalent doses are averaged, sex averaged, and this sex average equivalent doses are then used to calculate the effective dose as the tissue weighted average equivalent dose. Why do we need operational quantities? The effective dose is defined as an average over extended volumes and organs and bodies. It also depends on the direction of the incident radiation. In other words, effective dose cannot be measured with an instrument. From metrology, we know that only quantities defined in one point are measured by an instrument. The ICRU came up after the introduction of effective dose, therefore, with a definition of operational quantities. And generally, the definition of an operational quantity is the product of an absorbed dose at a point in a phantom at a depth d, weighted or multiplied by the quality factor, LT-dependent quality factor. So how does that compare? In the case of individual monitoring, we have the effective dose calculated the way I explained. In the case of the personal dose equivalent, one uses a very simple phantom, that is really a slab phantom, and one calculates in the anthropomorphic phantom the effective dose, and in the slab phantom the personal dose equivalent. Similarly, for area monitoring, the effective dose is calculated for a number of standard geometries, AP, PA, rotational, ISO, and so on. One gets therefore a number of curves, different curves for effective dose depending on the radiation geometry. In the case of the operational quantity, which is called ambient dose equivalent, H*10, the phantom is a sphere, the so-called ICRU sphere of 30 centimeters diameter, which is irradiated by a expanded and aligned field. Aligned means it's unidirectional, and it expanded so that the whole sphere is being irradiated, and the point is chosen to be 10 millimeters in depth in the direction of the incoming radiation. This slide sums this up, or compares. We always start off when we want to calculate these quantities, or their conversion coefficients rather. One starts off with a description of the radiation field, for example, fluence or karma in air. One uses the definitions of the effective dose of the one side and of the operational quantity of the other side, and then with the help of transport calculations, one calculates the conversion coefficients as function of the energy of the particle, and in the case of the personal dose, also as function of the incidence of the incident radiation. The conversion coefficients for the operational quantities are then used to calibrate dosimeter, for example, personal dosimeters, and the reading of these personal dosimeters is then, first of all, of course, HP, but this is then set equal in the records as effective dose. If one calculates such conversion coefficients here, there's the example for photons. It's two curves for the effective dose, one for AP, the other one for an isocentric irradiation. And then there's the personal dose equivalent, HP10, the red curve. You can see that in an energy range of about 50 or so keV up to 3 MeV, it gives a reasonably good approximation to the curves of effective dose, and therefore the operational quantities is in that case a good estimate of effective dose. However, at high energies there are problems. If HP10 is used to be calculated with the gamma approximation, that is the upper red curve, then above 3 MeV the difference to effective dose gets bigger and bigger. If a full-blown calculation, including the transport of secondary electrons, is included, then we get an underestimation of effective dose at high energies. And you probably noticed in the previous slide that there's a bump in the curve for HP10. This is reproduced here as green curve. The effective dose is shown here as blue curve. And the question is, why does the personal dose equivalent overestimate effective dose at these low energies by so much? And the reason is very simply explained. Effective dose is the average of all organs, also those deep-sitting organs, and therefore this includes organs which don't receive any energy deposition at all, any dose at all, whereas for the HP10, of course, the dose in 10 millimeter depth is calculated, and that depth there is still dose, and therefore you get this bump. It is perhaps interesting to note that if you put the dose equivalent for the female breast as function of energy, you get a similar bump, and actually you do it also for the male gonads. And the people who introduced the operational quantities at that time in the 80s were not unhappy about the bump from HP10 because it was contributing to an easier transition from the quantity which was used before the effective dose and the personal dose equivalent. That was the maximum dose equivalent. And of course, at these low energies, the maximum dose equivalent is with those organs which are near the surface, which is the female breast and the male gonad. Nevertheless, one has to realize that the personal dose equivalent overestimates the effective dose by a factor of 5. So first summary, the effective dose is used to control stochastic radiation effects with a single quantity, which is defined for the entire body, so it's a whole body quantity. It is calculated in an anthropomorphic phantom and averaged over organs which lie in different depths. The operational quantities are defined in one point and therefore are measurable. Provide a good estimate in energy ranges which were of interest at the time when they were established. And on the other hand, the conversion coefficients are evaluated in simple idealized phantoms, spheres and slabs, and they are calculated only for a fixed depth. For photons, the Kerma has been calculated with Kerma approximation, and at high energies, generally the operational quantities differ substantially from the effective dose. Now I would like to come to the ICRU report 95. That means the new definitions of the operational quantities for effective dose. The report itself also deals with operational quantities for length of the eye and local skin, but I will not talk about this in this I'd like to remind you, if you look at the ICRP report 116, which is the one on conversion coefficients for protection quantities, and you can see in paragraph 248 that it said that at higher energies there is a need to further examine the relationship of the operational and protection quantities because it was noticed that at the high energies which are dealt with in this report, the discrepancies get larger and larger. This recommendation in the ICRP report 116 was the starting point for forming a committee to review the definition of the operational quantities. The ICRU convened report committee 26, and which produced what is finally now the ICRU report 95, and the recommendation is now to define the operational quantity as a product of a field quantity, for example, influence, and conversion coefficient H sub phi. Then to derive the conversion coefficient from the same phantoms as effective dose. As you remember, the phantoms are very, very different in the two types of quantities. To illustrate or to explain that a little bit further, for individual monitoring, the ICRU report proposes to introduce a quantity called personal dose HP, H sub P, and that's defined by a conversion coefficient and influence, or the air camera. And the conversion coefficient is calculated as a ratio of the energy of the effective dose for an angle of incidence, given angle of incidence, and the fluence. That means the conversion coefficient is closely related to the effective dose, and therefore it is obvious that there will be a close numerical correlation between the two. Similarly, for area monitoring, the ICRU report recommends the introduction of the quantity ambient dose H star, which again is defined as a product of a conversion coefficient and the fluence. And the way it's done is in ICP 16 there are a list of effective dose for all types of irradiations, or directions of radiations, and of course for all energies and for many different particles. And the conversion coefficient is then simply the maximum energy of all the curves for effective dose divided by the fluence. Therefore, indirectly or implicitly, the conversion coefficient for H star is calculated with the phantoms, anthropomorphic phantoms. Here I'll show you as an example of the results. Like in the earlier slide, here is a curve given for photons as function of energy, the curves for effective dose for AP and ISO irradiation. Here you recognize the curve which I showed earlier for personal dose equivalent, and the green curve is the curve for the new quantity personal dose. And you can see, of course, that over the entire energy range, which is about, I think, 6 orders of magnitude, this new quantity is a very good estimator of effective dose. So what are the consequences for the dosimetry of these new definitions? Before I go into that, I would like to mention that the ICRU report 95 includes a comprehensive set of numerical data for conversion coefficients for many different types of particles and over large energy range, similar to the in ICP report 116. One example for personal dose, the conversion coefficients as function of energy from fluence to HP and HP10. For HP, the new quantity, it's the lower curve, the green. For HP10, it is the red curve, the upper one. And you can see that from energy above 50 or so keV, the two curves are almost parallel. That means instruments which are used in this energy range need only a simple recalibration. At the low energies, the ratio is varying, and the problem is a little bit larger. Now we'll look into that in a little bit more detail. Just note that there's an almost constant factor of 0.8 between these two quantities in this energy range, and people have said that will lead to an overall reduction of the doses which are recorded in occupational exposure. I will come back to that. The influence of the new quantities on the dose of record, first of all, as I say, it is whatever it's going to be, it is a better estimate of effective dose than before. One has to expect that the personnel which is exposed to low energy photons, that means in particular in diagnostic and interventional radiography, will see a reduction in their dose records. And then the question is, will there be a general reduction of this 20%, which you saw in the previous slide? And the answer to that is not really likely, because most people who are occupationally exposed have nowadays a dose reading which is actually 0, and therefore not 0 is entered in the dose record, but the detection threshold. And so only persons who receive a dose which exceeds the detection level will, relatively speaking, have a lower dose, 20%. The other argument against the new definition was we are losing conservatism. That means it is assumed that if you're having operational quantities which are overestimate the effective dose by quite a bit, that they are implicitly providing conservatism, and therefore that's good radiation protection. But I think good radiation protection practice makes use of the optimization principle and uses constraints and reference values to keep the exposure of the personnel as low as reasonably achievable. The right place for conservatism means for good radiation practice is in the procedures of the radiation protection programs and not in the definition of the quantities. Now, two slides giving you some results which have already been published using these new definitions. One is by Thomas Otto. In the upper graph, you can see response curves for an area dosimeter. The one with the new quantity is the lower one, and the green one is for the older one. And you can see they are totally parallel, and therefore a simple recalibration will solve that problem. The problem is a bit larger at lower energies. There the response will be too high at the lower energies in terms of the new quantity. But also that can be probably solved quite easily, at least this dosimeter, which is from the PHE in the UK, in a publication of Eakins and Tanner, they show curves for the response of HP10, that means the old quantity, for different angles of incidence, and the curves lie within the acceptance levels, the acceptance interval given by the IEC. If you calibrate this instrument in terms of HP, the new operational quantity, then you see here an over-response that's outside these limits. But the authors have seen by calculating some simple changes of filters for the TLDs will bring this response again into these acceptance area. So finally, to sum up, the new operational quantities result in a simplified and numerically coherent system. They provide a better estimate of effective dose for low energy photons, but also for high energy particles. The calibration procedures remain unchanged. There may be changes needed to introduce for the response. As I said, sometimes it's just simple new calibrations. Sometimes one needs to make small modifications for the design. There's no more ICRU sphere in this new concept, but that is not likely to be a big loss. The report was adopted as both by the main commission of the ICRU and the main commission ICRP in 2016. And I'd like to make one final remark or two final remarks. And that is, there was fear that if the report was published, that there would be immediately a problem. Everybody would have to adopt to the new recommendation, but this is of course not the case, because that is only necessary once these recommendations are adopted in a regulatory process and will become part of the new regulations. That is likely to take sufficient time for establishing modified calibration procedures and for adjusting the monitoring instruments, the dosimeters. As you have seen, there are already some publication on the practical consequences, and they show that the problems or the challenges are introduced by the new can be fairly easily overcome, and a comprehensive study of the consequences is currently carried out by a Eurodose working group. The report has appeared, as I said, it is appeared in December. It has it number 95. It is a joint publication by the ICRP and the ICRU, and is published in the Journal of the ICRU by SAGE. I want to point to the fact that there was, of course, a committee which prepared this report. It was chaired by David Bartlett and by Nolan Hattel. The list of everybody involved is in the writing. I will not read every name, but I would like to mention Günter Dietze, who was an extremely valuable member of the committee. Unfortunately, he didn't live to see this publication coming out, but we all will remember him as a very important member of this committee. And finally, I'd like to thank you for listening and watching. Goodbye.